What's up? We back. So yeah, this live stream has basically two main agendas. Let me just fix up my mic once. Yeah, so there's two agendas I will announce today. I'll first do a bit of background nostalgia. Maybe I want to learn how to use that breadboard thing and the meter I have with it. Right? Damn, this thing is a mess. Oh my god, did I just completely open it? Yep, I did. Okay. Fine. So firstly I want to learn how to use this meter that I have, right? And then we'll check out nvidia Cosmos and all. I need to just quickly get batteries from work. this epic torch. Like, it kind of saved my ass when I was trekking in Himalayas. But yeah, it got pretty dark and I used this torch to survive there. But this has good batteries. So let me set this up again. How do you know which is negative and which is positive? And this is giving me 1.44 volts. What's it supposed to give me? 1.5. Yep, it's pretty accurate. Yo, what is this thing even reading? What is even showing up on my screen? What? My application capture looks to be stuck, which is weird. Oh wait, my monitor capture looks to be stuck. Yep. It's working now.
Hi, this is Ben Finio with Science
this is
Buddies,
exactly
and this
what I
video
need.
will show you how to use a multimeter. Multimeters come in all shapes and sizes. While professional multimeters can cost hundreds of dollars, if you're a student doing a science project or a hobbyist just tinkering with electronics, a cheaper multimeter somewhere in the $20 to $30 range is probably all you need. Most multimeters have
Let me check how much this one costs, because this was gifted to me. Guess it won't show up in .in. Why does Amazon have its own search bar?
similar features including a screen that displays the readings, a knob that selects the measurement, and ports where you plug in the probes to take the measurement. In this video, we'll be using this DT830L digital multimeter, which is included in many of our Science Buddies kits. We'll go over how to measure voltage, current, resistance, and do a continuity check. Some of the most common features you'll use on a multimeter. Other multimeters might have more advanced features like the ability to measure capacitance, but we won't be going over those in this video. Most multimeters come with a pair of red and black probes with a plug on one end to go into the multimeter and a pointy probe tip on the other end that you can use to probe circuits. It's convenient to have some alligator clip cables handy, as those can allow you to clip onto the circuit to take measurements so your hands can be free to do other things. There are different types of probe accessories available. For example, these probes have a banana plug on one end to go into the multimeter and an alligator clip directly on the other end instead of a probe tip, so you don't need a separate alligator clip cable. So your hands can be free to do other things. A pair of red and black probes with a plug on one end to go into the common features you'll use on a multimeter. Other multimeters might have more advanced features like the ability to measure capacitance, but we won't be going over those in this video. Most multimeters come with a pair of red and black probes with a plug on one end to go into the multimeter and a pointy probe tip on the other end that you can use to probe circuits. It's convenient to have some alligator clip cables handy, as those can allow you to clip onto the circuit to take measurements so your hands can be free to do other things. There are different types of probe accessories available. For example, these probes have a banana plug on one end to go into the multimeter and an alligator clip directly on the other end instead of a probe tip, so you don't need a separate alligator clip cable. Let's start by looking at our multimeter instead of a probe tip, so you don't need to go into the multimeter, and an alligator clip directly on the other end instead of a probe tip, so you don't need a separate alligator clip cable. Let's start by looking at our multimeter in a little more detail. There are a lot of symbols on the front that might be kind of overwhelming and confusing at first, but don't worry, we'll go over them one by one as we use them. The main symbols you'll be seeing in this video are V for volts, A for amperes, which is the unit of current, and a capital Greek letter omega, which stands for ohms, or the unit of resistance. This multimeter has a separate on-off switch that you use to turn the multimeter on and off. More expensive multimeters usually have an auto power off feature that will turn it off automatically after a certain period of inactivity, but this one doesn't, so make sure you remember to turn it off when you're not using it in order to...
Weird. did the Arduino go? Here it is. Now this place is becoming a bit messy. So I have to look for the Arduino wire. There's a lot of wires in here. But this is the Arduino wire.
Conserve the battery. Now let's look at the ports where we can plug the probe in a certain period of inactivity, but this one doesn't, so make sure you remember to turn it off when you're not using it in order to conserve the battery. Now let's look at the ports where we can plug the probes into the multimeter. You'll see that we have 3 different ports labeled COM, V omega MA, and 10A. COM stands for common. That's where the black probe is going to be plugged in, and we'll usually connect that to the ground or negative side of our circuit. V into the multimeter. You'll see that we have 3 different ports labeled COM, V omega MA, and 10A.
Okay, now I need to write stuff down. So, just 1 second. I need to note all of this down. Right. So, first thing I need to do is get Obsidian out and attach a picture here. Okay, Apple ecosystem, quite epic. I should add an Excalibur file, right? Yep. So we're gonna put this over here. No, I do not want to put that as an embeddable. God damn it. Honestly, I'll just copy it at this point. Yep. So now time to go back to that video.
COM stands for common. That's where the black probe is going to be plugged in, and we'll usually connect that to the ground or negative side of our circuit. V omega MA stands for volts. Ohms or milliamps, we plug the circuit. V omega MA stands for volts, ohms, or milliamps. We plug the red probe into this port for most of the measurements we're going to be taking to measure voltage, resistance, or small amounts of current. And then finally, volts, ohms, or milliamps. We plug the red probe into this port for most of the measurements we're going to be taking to measure voltage, resistance, or small amounts of current. And then finally, we're going to be taking to measure voltage, resistance, or small amounts of current.
Why can I not re-edit this? This will take forever.
And then finally, this is taking to measure voltage, resistance, or small amounts of current. And then finally, this third one we're not going to use as often. That's for measuring large amounts of current up to about 10 amps. So for now, we're going to plug the red probe into this V omega. MA port. So for now, we're going to plug the red probe into this V omega MA port. Now let's start with the relatively simple case of measuring the voltage of a battery. I'm going to set the dial on my multimeter up here somewhere in the V range. I'm not going to worry about the exact number yet. Turn the multimeter on, and again I have the black probe plugged into the COM port and the red probe plugged into the V omega milliamp port. I have two batteries here, a AA and a 9 volt, and I'm going to start out with the AA. I'm going to take the black probe and touch it to the negative side of the battery, and the red probe and touch it to the positive side of the battery. And you can see I'm getting a reading of 001 on the screen. And that's not a very accurate reading. I'm not getting any decimal places, and you'll see that I have my knob set all the way up here to 1,000 volts, which, if you know anything about batteries, is much, much higher than we expect to get from a AA battery. We would expect this to be about 1.5 volts. So fancier multimeters will have an auto ranging feature where they will automatically select the measurement range for you. This multimeter isn't going to do that for you. You need to manually select the range that is the best for what you want to measure. So what I'm going to go do is go down a step to 200 volts and try again. And now I'm getting 1.5 volts, which is about what I expect, but 200 volts is still a lot bigger than what I need to measure. So I'm going to keep stepping down to the 20 volt range, and notice that when I do that I get an extra decimal place. The decimal point moved over 1. So now if I measure the decimal point to the 20 volt range, and notice that when I do that I get an extra decimal place. The decimal point 20 volt range bigger than what I need to measure. So I'm going to keep stepping down to the 20 volt range, and notice that when I do that I get an extra decimal place. The decimal point moved over 1. So now if I measure, I get 1.6 volts, 1.60. So my reading is getting more accurate. I got an extra decimal place. This voltage is actually small enough that I can keep going down. Now notice that the label here changed. Now I'm in the 2000 M range, which stands for 2000 millivolts. So now my reading is in millivolts instead of volts. It's important to pay attention to the labels on the dial because they'll tell you the units of your measurement. Now here, I don't have a decimal place anymore. I'm getting 1,608 millivolts. So as I keep going down, my reading keeps getting more and more accurate. If I go down too far, though, my range won't be high enough to measure the voltage. So I've gone all the way down to the 200 millivolt range. And now I'm getting a 1 with no other numbers, which is how this multimeter tells me that the reading is outside the current range I have selected. So if I go down too far, I'll get that 1 on the screen. I go back up to the next highest value, and that's going to give me my most accurate reading for this. I've gone. This is actually to measure. So I'm going to keep stepping down to the 20 volt range, and if I measure, I get 1.6 volts, 1.60. So my reading is getting more accurate. I got an extra decimal place. This voltage is actually label here changed. Now I'm in the 2000 M range, which stands for 2000 millivolts. So now my reading is in millivolts instead of volts. It's important to pay attention to the labels on the dial because they'll tell you the units of your measurement. Now here, I don't have a decimal place anymore. I'm getting 1,608 millivolts. So as I keep going down, my reading keeps getting more and more accurate. If I go down too far, though, my range won't be high enough more accurate. 8 millivolts. I don't have a decimal place anymore. I'm getting 1,608 millivolts. So as I keep going down, my reading keeps getting more and more accurate. If I go down too far, though, my range won't be high enough to measure the voltage. So I've gone all the way down to the 200 millivolt range, and now I'm getting a 1 with no other numbers, which is how this multimeter tells me that the reading is outside the current range I have selected. So if I go down too far, I'll get that 1 on the screen. I go back up to the next highest value, and that's going to give me my most accurate reading for this voltage. So in this case, I get 1,607 millivolts, or 1.607 volts. I can do the same thing for the 9-volt battery here, where you might be able to guess if I have this set to 2000 millivolts, that's 2 volts. That range is not high enough, so I get a 1. If I want to measure that 9-volt battery, I'm going to need to go up the next step to 20 volts. And here you can see that this battery has actually been drained a little bit. I'm only getting about 7.98 volts instead of the 9 volts I would expect. Finally, if I reverse my probes, so if I put the red probe on the negative terminal and the black probe on the positive terminal, I will just get a negative number. So that doesn't damage anything, it doesn't hurt anything, that just tells you that you have your probes backwards because you would expect a positive voltage when measuring the battery. Now, measuring the voltage of a battery is pretty simple. What if we want to measure the voltage of something in a circuit? So here I have an example circuit consisting of a battery pack, a resistor, and an LED. Very simple demonstration circuit. And what if I say I want to measure the voltage in this circuit? Now, note that voltage is measured between 2 points, so it doesn't make sense to just ask what is the voltage in this circuit. We have to ask which component we are measuring the voltage of. In this case, if we look at the circuit diagram, we can see we have 3 components in series. We have the battery, the resistor, and the LED, and we can measure the voltage across any one of those components individually. To measure voltage in a circuit, you connect the multimeter in parallel. So in this case, there are 3 different ways we could connect the multimeter in parallel to something in this circuit. We could connect it in parallel to the battery, in parallel to the resistor, or in parallel to the LED. When taking measurements on a breadboard, this is where alligator clips and jumper wires can come in handy because you can just put the jumper wires into the breadboard and then your hands will be free to do other things. If you don't understand how a breadboard works or you've never used one before, we highly recommend you check out our breadboard tutorial video, which will tell you everything you need to know about breadboards. But for now, we're going to assume you know how they work. So first I'm going to connect my 2 wires in parallel to the battery, putting them into the power buses here. You'll see I get a reading of 2.83 volts. I can also connect them in parallel to the LED. I get a smaller reading of 2.2, roughly about 2.3 volts. And finally, I can connect them in parallel to the resistor. And I get a reading of about 0.65 volts. So as I would expect with these components in series, the voltage across the LED plus the voltage across the resistor should equal the voltage across the battery pack. Now, what if I want to measure the current through this circuit? This gets a little more complicated. To measure the current through a part of a circuit, you need to put the multimeter in series with that part of the circuit. And while to measure voltage, I didn't actually need to rearrange anything on the breadboard to do that because I was just putting the multimeter probes in parallel with the different circuit components. To put the multimeter in series, I'm actually going to need to rearrange things on the breadboard a bit. So if I look at the circuit diagram, I only have 1 loop in my circuit here, so the current I measure is going to be the same regardless of where I put the multimeter. I could put it in between the battery and the resistor, in between the resistor and the LED, or in between the LED and the battery. The current will be the same in any case. But when I go do that on the breadboard here, I'm going to need to move one of the parts. So for example, I'm going to move the resistor lead over 1 hole here, and then get ready to put my multimeter probes in series with the resistor and the LED. But before I do that, I want to be careful. Let's go back and look at the ports for the probes on our multimeter again and the settings for current. Remember, we have this extra port for 10 amps. And if you don't know how much current you're going to measure, it's always safer to start with that 10 amp setting because that will allow you to measure a much higher current without damaging your multimeter's fuse. So if you know about LEDs, you might know, oh, that's probably only a couple tens of milliamps, you should probably be safe. But especially if you're working with motors or something where you just in general don't know the current, it's safer to start with that higher measurement because, as you can see, if you look at the small print by this other port here, that one is limited to 500 milliamps max. So if we exceed 500 milliamps on this port, we're going to blow the fuse. So we can go all the way up to 10 amps on this one. Safer to start there, and we're going to turn our dial over to the 10 amp setting on the knob. So now I should be able to put my multimeter in series. You notice that the LED has gone out because I broke the circuit by moving that resistor.
Yeah,
I put the multimeter in series here, the LED goes back on.
Where this should be.
But I'm getting a pretty inaccurate reading again. 0.01, I don't know what the decimal points are beyond that, so I should be safe now to move down to the port with the lower current range that's going to be more accurate. So I'm going to switch back down to here, lower myself to the 200 milliamp setting, and you can see range that's going to be more accurate. So I'm going to switch back down to here, lower myself to the 200 milliamp setting, and you can see now I'm getting a more accurate reading of 13.7 to 13.8 milliamps. And just like I did with the voltage, I can keep stepping down to get more and more accurate readings until my range goes too low. So I can step down to 20 milliamps. Now I'm getting an extra decimal place, about 12.21, all the way down to 2000 milliamps, and now I've gone too low. Okay, so if I go back up to about 20 milliamps, that's going to be the most accurate reading I can get for this circuit with 2 decimal places. Now, when you are done measuring current, it is always a good idea to set your multimeter dial back to measuring voltage. And that's because it is much easier to accidentally blow the fuse when you have the multimeter set to measure current. For example, if you wanted to measure the voltage of a battery like we did earlier, and you connected the probes directly to the battery with no resistance in series to limit the current, while you have it set to measure current, you will easily blow the fuse because you're going to get a lot more than 500 milliamps directly out of the battery. So again, when you're done measuring current, set it back to voltage just to be safe the next time you pick up the multimeter. Okay, next let's talk about measuring resistance. So this is something that's convenient if you just hate reading those color codes on the tiny little resistors, or if you need to measure the actual value of your resistor instead of just the rated value, because there's usually a pretty big error range, like 5 or 10% on the actual value of the resistor. So to do that, you're going to want to remove the resistor from the circuit. Don't try to measure resistance while the resistor is connected to a power supply in an active circuit, or you won't get an accurate reading. And again, here's where alligator clips come in handy to just clip onto the leads of that resistor. And just like we did with voltage and current, you can make an educated guess as to where you should start on this dial. So for ohms, we can go all the way up to 2000 kiloohms, which is equivalent to 2 mega ohms, or all the way down to 200 ohms. In this case, I started at the lower end of the range, and I have what should be a 47 ohm resistor here, so I'm getting pretty close to that, about 46.8, 46.9 ohms. And you can see as I go up, I start to lose accuracy because I'm losing that decimal place. So measuring a resistor this small, I want to be all the way down there in that 200 ohm range. I have a bigger resistor here. This one is supposed to be about 10 kiloohms. So if I connect that, you can see I'm getting the 1 because I'm outside the range. I've exceeded 200 ohms. And as I start going up, eventually I should get in the proper range for this resistor. So you can see again, there's that error percentage. This is actually about 10.3 ohms, not exactly, sorry, 10.3 kiloohms, not exactly 10 kiloohms. So it can be important, depending on what you're doing, to measure the actual value of your resistors. Now, with cheaper multimeters, you're not going to get very accurate readings for very small resistances. So if you're trying to measure something just like a wire, this is usually probably down around 1 ohm or even less than that. Don't trust those readings too much. You can see I can connect to this wire and go down to my smallest range, and I get something like 1.0 ohms, but really below an ohm, your reading is not going to be very accurate with a cheap multimeter. So make sure you use this to measure actual resistors, but not just pieces of conductive metal or wires. The final feature we're going to go over is the continuity check. So that's this little symbol here with kind of those little curvy lines and the arrow symbol, which represents a diode, if you know what a diode is. And this one is a really convenient feature that just beeps if two things are electrically connected. So if I touch my probes together directly, it beeps at me because there's a complete conductive path for the circuit, or the current to flow through the circuit there. This is a really convenient feature to check if two things are connected like they're supposed to be in your circuit, or for example, to check if a cable is good. So for example, let's take my circuit here, put my resistor back in, And say I don't know if maybe I have something wired improperly. I want to make sure that there's a conductive path between this leg of my LED and this wire on the battery. So that's telling me that there is a path between this part of the LED and there. So say I had this wired improperly, say I had the resistor in the wrong hole, and my LED is not lighting up, then I can test both sides of my LED. I can test here and say, okay, I know I have conductivity on this side. Those are connected because I'm getting a beep, but if I test on this side, there should be a connection between the LED and the resistor. But I'm not getting a beep there. Then if I look more closely, I could realize, oh, I have that wired improperly. I don't have conductivity between this leg of the LED and this leg of the resistor. Similarly, say you have an experiment with a bunch of wires or cables and you're not sure if maybe you kinked a cable or broke something, or if you have a cable that's going bad. If I take this alligator clip and touch the probes to both ends of the alligator clip, I'll get a beep letting me know that my cable is good. If I didn't get a beep, then I'd know that this cable is probably bad. So again, a convenient feature that you can use to test for conductivity in circuits, or test if a material is conductive. For example, if I touch these two probes to a piece of metal, say like the outside surface of this battery, I know that's conductive, but if I touch it to the paper on my work surface here, that's not conductive because paper does not conduct electricity. So also a convenient check to test if a material is conductive or not. Again, there are some more advanced features on this and other multimeters that we didn't go over in this video. You might have noticed this NPN and PNP thing down here, that's for measuring transistors. There's a V with a squiggly line next to it for measuring alternating current instead of direct current. You can measure the voltage from a wall outlet. We don't recommend doing that if you're new to electronics because wall outlets are actually dangerous and you can hurt yourself if you don't know what you're doing, whereas the electricity from batteries and little battery-powered circuits like this is generally pretty harmless, so this is much safer if you're starting out. We're not going to go over those in this video, but if you have any more questions about anything you saw in the video in more detail, we recommend you check out our written tutorial. There was a link to that at the end of the video, and have fun using your multimeter in your project.
Okay, all this happened because I wanted to learn how to use a breadboard, right? Yep, so that's done. Multimeter. I have an idea of how to use this now, but a breadboard I'm still not.
Diagram as well as on the actual component. Okay, so now we know that this pin is detection mode and hold each probe to one end of the resistor you want to test. As you can see, it's to get those signals into and out of our circuits. You can use 3.5mm ones if you prefer, but I'm going with big 6.35mm sockets. Now, in order to connect these with your breadboard, you've essentially got two options. If you're comfortable with a soldering iron, you could simply solder wires to the socket's connectors. But in case you're not, you can always fall back on alligator clips like these. Just attach them to the connectors and to a small jumper, and you're good to go. This next tool is not exactly necessary, but it will save you a lot of headaches, especially while troubleshooting. A simple digital multimeter. With it, you can measure all kinds of things. The voltage between 2 points, or the amount of current flowing, or the resistance value, or even an oscillation's frequency. Super useful. But okay, time to talk meat and potatoes. Here are some of the main components you'll be dealing with when building synthesizer circuits. First off, let's check our resistors.
So it's one of the most time-taking things about this electronics thing is that I forget the concepts for voltage, current, and resistance every time, and how they're related. I had a pretty good ChatGPT explanation for that. Yep, this one. Good stuff. Yep, this one was very nice. So we have two charges. This guy told what's the force between those charges, and then this guy created a battery which is a continuous source of electricity. His work led to the concept of electric potential, which is the difference in potential energy per charge between 2 points. Voltage, named after what was eventually known as the electric pressure that pushes charges through a circuit. Just think of it like that relationship. This comes from the idea what was the okay, interesting. That if voltage is energy per unit charge, then the total energy work a voltage times the amount of charge moved. The more amount of charges we have, the more the voltage. The voltage will be the same, right? Yep. The more charges we have, the more energy we'll have, but then we have more charges. Ohm's law. So now describes the relation between voltage, current, and resistance in a conductor. V is equal to IR. For many materials, the current through conductive proportional to the voltage applied. The resistance derives through careful experimentations. Conventional current electrons in the positive vicinities. Positive vicinity is known as positive charge going from positive to negative, which is like technically true. It's shown to flow in that one in diagrams, but card diameter is true confusing. It's just not practical possible with every sign. If you want to break all signs and have a few tickets all things we say or imply or at least the whole idea of an electron current being electrons moving generally encourages a widely naked. Electrons in household copper wiring is comfortably measured in single-digit meters, not kilometers per hour. Bruh. What do you think of an electric current in solid and velocity electric field string stuff? Some substantial fraction of C. In mathematics in general, it's a way to portray some natural type body. That's true. So it's not the electrons flowing. It's the electric field doing something. Just like the fields there's like this. There's like these levels of humans. Some on the top who figured out this electric fields and how in general matter comes out of distortions in fields are just so above the rest in terms of intelligence. It's like they're different animals in themselves. It's like a dog and a human. It's very hard to understand how people who figured this stuff out think the way they do. This is the push pressure. This is how much it is resistive at. The energy is W. Let's get that for energy is related to matter. That makes sense. This goes more into theoretical physics than practical physics. I'm kind of all these is literally just the most, it's like going in a line from practical physical applications to going into theoretics and what everything means and going down the ladder of abstraction until you're thoroughly confused what the hell you were even doing. This is just simple rules, and this goes down into the abyss of what are we. It's quite cool. The voltage is energy per unit charge, and okay, eventually formulating that way now. Joule's law of heating. Electrical power is related to the current and resistance in a conductor. What was power again? Rate at which energy is transferred or used. So voltage is energy per charge, and I is the rate at which the charges are moving, right? I'm pretty sure that's true. Measure the amount of electric charge in motion per unit time. Yep. Amount of electric charge. Rate of electric charge flowing, and this voltage is Energy transferred or used per unit time. So work should also be in joules, right? Unit of energy, unit of work. Yep, they're both joules. ChatGPT gave me the best explanation I could have ever asked for. I think that's it for today. I still have to do this controlling LED, but just had a bit of theoretical and, well, a bit of practical catching up. So yeah, it's a pretty slow process, but yeah, I'm starting to get in the groove, I guess. It's not the end of the stream though, because I'll also be checking nvidia Cosmos. But before that, I'll pack this stuff up, and I have to check my graph, of course. Bruh, just open that sexual selection. Oh my god, that's a lot. Yep. The biggest part of this graph is still the grappling stuff, right? Learning a lot of that, although I still suck at it. But then we have some nodes like fast AI, right? And then some other nodes like behavioral biology lectures. A lot of it is just biology lectures, and then a lot of them are actually the biology lectures. So much stuff. The voltage, the Arduino stuff, actually, where is that? The fuck is this? Where is the Arduino stuff? Yep, here. So many concepts in my brain. Interesting. Just a fuck ton of stuff, all from different domains of knowledge and information, all somehow connected to one physical world on different levels of abstractions. Kinda crazy to think about, huh? Leave it. It's just a small node, but it's pretty cool. I'll just go take a piss. Then we'll be back. I have returned. Time to put all this inside. You know these pins, they're kind of what they look like. These little pins, they're like, you know, when like a girl has like these sleeves, but they're all the way up here and their hands are just kind of outside. Like one scene in Breaking Bad when Skyler was telling Walter how she called his mom, and apparently his mom didn't even know that she had cancer, and she was doing that whole mean girl, you know, just that whole scary wife thing. But then it kind of looked cute because her hands were inside, and it's just one of the things I guess I like. So when these pins are like up like this, see, it looks like that. It looks like a cute girl with sleeves above her hands. Interesting. The worst thing with this whole setup is that you have to put it back inside, and that's too much work. But anyway, I am liking this. I'm actually enjoying this whole thing. It's fun. especially building up concepts and especially writing them is very good. So only so much stuff you can do throughout a week. I've got lots of other things I am involved in, and there's always this thing in my mind that what if I'm literally falling into that trap of too many cooks ruin the dish. But yeah, doing this stuff on the weekends is actually pretty nice. I can give it a bit of time, not too much dedication, like that's 1 or 2 hours max every week, but I can understand if this is something I want to pursue more later on. Things that I might want in life might not always be possible. It's one thing my grandmother told me. It's sometimes what you want to do, even if you do everything correctly, sometimes you still can't do it because other responsibilities come up in life and you just gotta accept it then. But well, as long as I am capable of trying to explore and see what I want in life and where I want to get in life, I should do that at least till I can, right? Oh my god, how am I ever supposed to put this back in? It's too complicated. And if I put it back in and I find that something is missing that I also had to put in, I will flip. Oh my god, I'm pretty sure half of this is broken already because of my absolutely epic skills at packing this back up, which is always a pain. Okay, this wire goes inside, right? Spaceonomics. This should also be a study somewhere. Wonder if companies actually study this to cut on like packing wastage and stuff. How to put different things best in a space, like spatially. Okay, time to pack the multimeter now. Multimeter is a bit easier to pack because, well, these cords are not that hard to just put inside this box. God damn it. Even the multimeter isn't the easiest thing to pack. I remember now what a multimeter used to be. It was the combination of an ammeter and a voltmeter, or whatever they taught us, I guess. Okay. Oh yeah, I have this industrial engine thing playing in my Safari, by the way. It's very nice. I do have so many streams. Okay. So, time to check out nvidia CUDA. Isn't that right? No, nvidia, what was that again? Nvidia Cosmos, right? Thinking I should spec into this a bit because it's kind of aligning with what I want to do later on.
The next frontier of AI is physical AI. Model performance is directly related to data availability, but physical world data is costly to capture, curate, and label. NVIDIA Cosmos is a world foundation model development platform to advance physical AI. It includes auto-regressive world foundation models, diffusion-based world foundation models, advanced tokenizers, and an NVIDIA CUDA, an AI-accelerated data pipeline. Cosmos models ingest text, image, or video prompts and generate virtual world states as models ingest text, image, or video prompts and generate virtual world states as videos. Cosmos generations prioritize the unique requirements of AV and robotics use cases, like real-world environments, lighting, and object permanence. Developers use NVIDIA Omniverse to build physics-based, geospatially accurate scenarios, then output Omniverse renders into Cosmos, which generates photoreals, then to build physics-based, geospatially accurate scenarios, then output Omniverse renders into Cosmos, which generates photoreal, physically based synthetic data. Whether diverse objects or environments, conditions like weather or time of day, or edge case scenarios. Developers use Cosmos to generate worlds for reinforcement learning AI feedback to improve policy models, or to test and validate model performance, even across multi-sensor views. Cosmos can generate tokens in real time, bringing the power of foresight and multiverse simulation to AI models, generating every possible future to help the model select the right path. Working with the world's developer ecosystem, NVIDIA is helping advance the next wave of physical AI.
So it's just a video generation thing. Not just, obviously, it takes a lot of power, I guess. First wave of our first versions of pre-trained models. So they're using, so they used a lot of physical data to train an AI to create more physical data on which to train physical movement AI. Kind of trippy. Need a tutorial to use these. So, how do we get started with this? So open weight is when you only tell the weight and not the whole process of getting to those weights. Interesting.
I spent a lot of the last year studying math, computer science, and all sorts of academic things. And while this is really interesting and things that I think will be useful throughout my career, I think it was a mistake. It was not the best use of my time. In this video, I'm going to go over what I learned, what I studied, and most importantly, what I would do next time if I could start over. So it was November 2023, a little over a year ago, when I decided I was bored with web development. I wanted to do something different. And I thought, AI sounds great. And so I picked up a couple books. This one, Deep Learning. So it turns out it is a graduate level math textbook series. And this on discrete math is pretty great.
I have Git LFS already, right? Okay, cool. Let me try this. I completely forgot my Hugging Faces username. Wait. Okay, so my username is Martian Cactus. Why is this weird username / password type authentication? Why did it tell me to do remote authentication then? What is wrong with you? Okay, so when it asks you for this password, you give the access token, is what these guys are telling me. Okay, bye bye again, guys. I will just get the access token from where I saved it. This keeps showing that remote access is not allowed. Weird. Okay, whatever. I'm done with this setting. I'll do this next week. We'll make this thing a weekly thing. Yep, okay. I'm out. It was fun stream.